And this is basically how strong is that force? How strong is that electrical driving force? And that is going to depend on two things. That is going to depend on the strength of the membrane potential right? The strength of the membrane potential, right? Or the degree of the separation of charge. If you have more negative on the inside of the cell, more positive on the inside, on the outside of the cell, how strong is that separation of charge? How strong is that membrane potential, right? The second factor that is going to depend on is the amount and the type of charge on the particle in question. So the amount and the type, whether it's positive or negative, of charge on the particle in question. Okay? We can have sodium that has a positive charge, and it's a monovalent cation. What do I mean by monovalent cation? Anyone? What do I mean by monovalent? The number of charges, right? So this is a monovalent cation. It has one positive charge. Potassium is also a monovalent cation. Calcium, on the other hand, has two positive charges. Therefore, it's a divalent cation. So the strength of the electrical driving force is going to depend on how, what amount of charge is on each of those particles. Okay? If it's a monovalent cation, it's going to have not as great of a force as if it's a divalent cation. Okay, we'll see that in a minute. So let's look at a scenario here. We got 3 cells. Okay, we have some negative ions in the side of this cell, positive ions outside. The membrane potential here is, let's say, negative 60 millivolts. In our second cell, we have a similar scenario, but we have more anions inside the cell, and then we also have more cations outside of this cell. And the membrane potential here, what's the membrane potential going to be? Is it going to be bigger or smaller than that first scenario? What is our membrane potential going to look like here? We have a greater separation in charge because now we have more anions inside the cell, more cations outside the cell. So our membrane potential is going to be twice as much. So let's say negative 120 millivolts here. Okay, we have a greater separation of charge. On the third scenario, we have anions in the cell and cations outside, and a similar membrane potential as in that first cell. So negative 60 millivolts here. Now in this first cell, let's take the movement of sodium into consideration. And because we have negative ions inside the cell, we got positive ions outside the cell. Sodium is a positively charged ion, right? It's a cation. And so it's going to be attracted to the excess anions inside the cell. And so the electrical driving force is going to want to move sodium into the cell. Okay? Now let's take another scenario with sodium. For this cell, the membrane potential is negative 120 millivolts. So there's a greater separation in charge here. What does that greater separation in charge tell us? What does that greater separation in charge tell us?
The inside more negative.
The inside is more negative, right? And what's sodium going to want to do? Right, sodium really wants to get inside. Because of that greater separation in charge, we have a stronger magnitude of the electrical driving force here. All right, and I put 2 arrows to indicate that stronger force. Okay, so here I'll say greater separation of charge equals a stronger or greater electrical driving force. Okay. Let's look at a third scenario. So our third cell, we also have a membrane potential of negative 60 millivolts here, but let's take a different ion into consideration. Let's look at calcium. Okay, we said calcium is a divalent cation, meaning that it has 2 charges. And so even though we have a membrane potential, very similar to our first cell, we have a stronger force that's created because we have a divalent cation. Okay, can everyone understand that? We have a stronger force created in this third cell because our cation now has 2 positive charges. And so we also have a stronger electrical driving force. Okay, even though that membrane potential is the same as that first cell. Okay, so I'll say greater charge on the particle in question equals a stronger electrical driving force. So these are the 2 factors that affect the strength or the magnitude of the electrical driving force. One is going to be the strength of the membrane potential, right? How much separation of charge do we have? The second is going to be the amount of charge and the type of charge on the particle in question. Whether it's divalent, whether it's monovalent, whether it's positive, negative, and so on. All right, any questions on this? Okay. Oops. Okay, so that pretty much sums up us differentiating the chemical driving force and the electrical driving force. And now we're really going to start to put these 2 forces together and talk about the electrochemical driving force. So this is the sum of the chemical and the electrical driving forces. Okay? We talked about them separately, but I really want you to understand that in reality, the movement of particles across a membrane is under the influence of both these forces at the same time. Okay, so in reality, both of the forces affect the movement of particles across a membrane. Okay. Now, let's determine which of the forces, actually, let's go back a slide, and let's talk about this scenario here. So in this scenario, we have a cell, and the membrane potential here is negative 94 millivolts, which simply means that there's an excess of anions inside this cell. So it's more negative inside and it's more positive on the outside. Now, in this scenario, we're taking the movement of potassium into account. And as you can see, there's a concentration gradient for potassium where there are 6 potassium molecules inside the cell, and then there are 3 outside. So we have a concentration gradient established here. And so potassium wants to move out of the cell in accordance with that concentration gradient, or the chemical driving force. On the other hand, because of this separation of charge, potassium is positively charged, and so it really wants to get away from all of this positive charge on the outside of the cell, and it wants to go into the cell where there's an excess of its opposite charge, right? Negative.